Welcome to our exploration of Wavy curve theorem. It's a fundamental concept in calculus that helps us understand the behavior of various functions over an interval. In this video, we will be more focused on polynomials rather than a general function. Now let's see. Firstly, we have a second degree polynomial, often called a quadratic function. These are the functions that are widely used in the real world problems such as projectile motions and shapes of many satellite dishes. Now let's examine a third degree polynomial. This polynomial is often referred as cubic polynomial. Its graph can take various shapes, including one or two bends depending upon the coefficients. These are also used in many real-world problems. Now as we move to higher degree polynomials, the graph become more complex. These polynomials can exhibit a wide range of shapes, including multiple peaks and valleys. Now our agenda for making this video is that to answer a question, how can we determine sign of a polynomial over a specific portion of real line? To answer that question, let us firstly observe a 1 degree polynomial and its behavior. Now you can clearly see from the graph of this 1 degree polynomial that across its roots it is not changing its sign. On the left hand side the sign of this linear polynomial is negative, and on the right hand side the sign is positive. That means on one side the sign will remain same and on the other side sign will change. If it is negative it will become positive, if it is positive it becomes negative. This happens for a linear polynomial. Now, let us take an example where we will try to understand the same concept for a higher degree polynomial. Now, as you can see, we have a 3 degree polynomial and we have factorized it. That means your 3 degree polynomial is actually a combination, or we can say multiplication of 3 linear degree polynomial. That means the behavior that linear polynomial will have will be similar kind to this of 3 degree polynomial, right? Now firstly determine its roots. We have 3 roots, 0, -1 and -2. Now let us plot these roots. Because of these 3 roots, we are actually able to divide our Cartesian plane into 4 regions. Now let's talk about the first region. On the first region, we have 3 factors with this. The first factor is x. On this region, x is positive, x plus 1 is also positive, and x plus 2 is also positive. Because all 3 are positive, therefore their multiplication will be also positive. That means on this region, we are going to have a positive sign. Now let's talk about our second region. On this second region, our first factor x will be negative and the remaining 2 factors will be positive. Now product of these 3 will be negative, so therefore final sign of our polynomial on this region will be negative. Similarly, we can examine same thing for the remaining intervals also. Now, because you have divided your Cartesian plane into 4 regions and you know the specific sign of your polynomial on these 4 regions, therefore you can draw its graph. So you can see On the first reason it is positive, then it is becoming negative, then it is becoming positive, and then it is becoming negative. That's why we say a polynomial is just like a wave, but once its roots are finished, it's not going to behave like a wave, it's going towards positive infinity or minus infinity. So using this we can actually understand why polynomials actually behave like waves on some portion of real line. It is because its linear factor, if we can factorize our polynomial into linear factors, its linear factors showing a particular sign, and that helps us to determine the sign of that polynomial over that interval. So our question is answered, but what I am leaving you with, I am leaving you with one more question. If your polynomial is not going to get factorized version, that means your polynomial is not, your polynomials is a polynomial with complex roots, then how you can determine the sign of that polynomial function over some specific portion of the real line? That's my question to you. You can answer it in comments. Thank you so much.